Okay, so we talked about unit hydrographs last time, and to get a unit hydrograph, what you'd have to do is you'd have to put a rain gauge in the field, and you'd have to have a stream gauge on a stream, and you'd need to yourself characterize a certain storm and what actual physical response it had coming out of that watershed. And so once you know the amount of rainfall excess that's available and the stream's response to that rainfall excess, then you can linearly scale it as long as the storm that you're predicting is the same duration as the storm that you measured the first time around. And so that's not always going to be the case. It may be that during a period of observation, the best storm that you have data for was 2 hours in length. And what if you want to predict what's going to happen to a 4-hour storm? So part of what we're going to do today is look at how to translate a different duration storm. But before that, there are ways that we can, even if we have no storm data at all, no physical measurements of what the unit hydrograph is, you can synthesize a unit hydrograph just based on the physical characteristics of a watershed. So you just sometimes don't have the realistic data, and so you have to synthesize using geometric or statistical procedures. And so the Snyder synthetic unit hydrograph method assumes that you're going to have a triangular hydrograph of runoff. And think about the curve that we've seen before. It's a lot more smooth with a gradual increase coming to a peak and then gradually tapering down and slowly returning to the base flow. Snyder synthetic unit hydrograph doesn't allow for that kind of characterization. It just assumes that you have a linear increase to a peak and then a linear decrease back down to the base flow or back down to the zero flow rate. And so what we'll do is we'll have a time of rainfall as a given in a problem statement, or it's something that we would begin with when we're trying to synthesize a hydrograph with this. Certain time to peak that can be calculated based on the physical parameters of the watershed, and the peak flow rate is based on those factors. And so just as an example of how to do Snyder synthetic unit hydrograph, I'm going to show you the calculations. Normally I'd have the students do the calculations, but since we also have to get to the S-curve method today, we're going to just speed through this a little bit more quickly than normally. For a given watershed area in square miles, and if we know the length of the main channel, and so that would be the longest stem in the watershed that it actually has stream flowing in a concentrated channel. Now this geometric parameter, the length from the outlet to the centroid of the watershed, if you have a relatively circular watershed, then that would be pretty small, but if you had a really long, narrow watershed, then this length to the centroid would increase. And the regional parameters are kind of tuned, like if you are working in a place that the Snyder synthetic unit hydrograph is utilized in other watersheds, then you could look up the regional parameters based on the calibrations that have been done in other watersheds. And so let me pull up the calculations for the Snyder method just to show you what it looks like, how we do the substitutions. I think you might have a homework problem related to the Snyder method. So it's kind of a step-by-step procedure. I'll put this PDF on Blackboard so that you can have it as a reference when you're working through the homework assignment. Jeffrey, do you have a question? Oh, okay, that's all right. Just want to make sure. There is the first step is you're finding the time to peak by using the regional parameters, and the equation is slightly different depending on if you're using SI units or British gravitational units. And so you'll notice here that I've defined that if you're working in BG units, you use miles. SI units, then you'd substitute in kilometers for the main channel length and for the length of the stream channel, the centroid length. So the first thing you do is you calculate the time to peak, and then you'd calculate, calculate the time to peak for the desired storm duration. So the standard storm, let's say if the standard storm is 1 hour, but you want to know what the hydrograph would look like for a 2-hour storm, then you have to convert to find the time to peak for your desired storm duration based on the input of the rainfall data that you have available. And if you know, for instance, that it's like a 90-minute storm, then you'd have to transform to find the T sub PR. And then the peak discharge is going to be based on that time and also on the area. And so it's scaling linearly based on the area of the watershed. And so the peak is just based on, we don't have any, the C values here aren't related to the runoff coefficients. These are just like time parameters. And so we don't know anything about this watershed in terms of the soil type. We don't know about the land cover, the percent impervious. This is just only applied for a rural watershed where you have these regional parameter data, like the C sub T and the C sub P. Those are the parameters that would take into account what kind of soil you have and what kind of land use characteristics. And so I just want to point out that here, when you're finding the unit peak discharge, that isn't accounted for in the formula directly. It's an indirect effect. And the C values here don't really have any meaningful units. So once you know the Q sub PR, what that's showing you is how high the peak is for an inch of rainfall excess. And the question then is the width of the triangle. How long is it going to take for it to get back down to zero flow rate? And so I'll point out here that T sub B is the bottom width of the triangle, where Q sub PR is the height of it. So you're what you're calculating is based on regression of other watersheds, the area of your watershed. You're finding out how long until the peak occurs, the height of the peak, and then the overall length of the unit hydrograph. So this handout that I'm going to put on Blackboard for you kind of summarizes the approach. And so then in the specific example that we've got, you would calculate the time to peak with the known geometric parameters and the coefficients having to do with the units, transform the T sub P into the T sub R, which is the standard storm duration. You then calculate the time for the desired storm duration, calculate the height of the peak, and I want to point out that the units here, in this case 552, that's the CFS per inch of rainfall excess. And then the W50 and W75 is just kind of the geometric parameters that's showing how wide the hydrograph is at a certain flow rate. And so, what's the flow rate at 75% of the peak? What's the width of the hydrograph at 50% of the peak? So that we know the shape of the triangle, and then the base length, this T sub B here. There's the formula to calculate the width of the hydrograph. So in the end, what we would want to have as an output of the synthetic unit hydrograph is how tall is the peak, how long from the beginning of the storm until you see the peak, and then when does the flow get back down to zero. So the handout I'm going to put on Blackboard kind of works through that, and I'll include these calculations along with it, just so you can have an example and an illustration of how it fits together. That's the synthetic method. But the other thing we need to take a look at is how to transform hydrographs. And this is a complex procedure that has to do with, if you have a unit hydrograph that's based on a measured storm duration. So for instance, if you observed a 2-hour storm, but what you want is you want a unit hydrograph that would correspond to a longer storm duration. So this is a spreadsheet procedure that we can go through to transform what a hydrograph looks like over one period to the runoff that you're going to experience in another. And the procedure is that you repeat the storm several times. And so I want to point out that this first segment up at the top of the figure here, that relates to the rainfall hydrograph for our beginning storm, the 2-hour storm. And then this first curve is the runoff hydrograph that is in response to the first pulse of rainfall. And what we're going to do in the spreadsheet method is we're going to repeat the 2-hour storm back to back to back over and over indefinitely. And if you repeat those storms indefinitely but then you overlay them, you'll notice that when one of the hydrographs is going down, the next one is coming up, and so the overall S-curve is just the addition of all of these successive unit hydrographs that are staggered back to back. And so here's the example that we're going to work through. We're going to say that if we have an inch of rainfall excess that fell during a 2-hour storm, then this is the hydrograph we got out of it. What we're going to try and do is transform that into what if it was an inch of rain that falls during a 4-hour period. Then I want to show you the procedure that we would follow to create that S-curve. And so if you've got Excel started up on your laptop, you can log into the machines there, and we'll go through that process together. Give me just 1 second here. All right, so here's our original hydrograph. So let's key in that data where at the top we're going to have our time, and then the 2-hour unit hydrograph is CFS per inches of rainfall excess. Remember, rainfall excess is the difference between rainfall and then the infiltration and abstractions. So we'll put in the original unit hydrograph that we had, which was during a 2-hour period, what's the runoff going to be from this watershed? So 0, 69, 143. All right. So you'll notice in the handout that I've given you that we have many different columns, and there's no fixed rule on how many columns you need. What we're looking for is we're looking for the sum to plateau and stay at some constant value for a couple of periods. And so, you know, we may need to have, depending on which hydrograph we're starting with and how long it is, you may need to have more than 11 columns. And so 11 isn't the magical number for this, but let's just make the width of those columns a little bit less so that we can see everything on the page at once. Okay. Now, what you do is you're just going to lag by 2 hours, because this is a 2-hour unit hydrograph. And so what we're going to do is, does everybody have the original hydrograph typed in? So just copy the whole thing, Control-C to copy, and then paste it delayed by 2 hours in the first column, so Control V. And then for the second column, you delay it again by another 2 hours, so you just paste. So we're pasting down, and then you paste a third time. So you just keep lagging by an additional 2 hours with each column. Okay, now the S-curve is going to be the sum of all of them. Now if I go back to this example, remember what we've done is we've said instead of just having one rainfall and one response, we're going to have rainfall back to back to back. So what would come out of the watershed if we just had an inch of rainfall excess every 2 hours? So if you had an inch of rainfall excess every 2 hours, this would be the first response that you had, but then it rains again at the beginning of time 2, and so then you'd have this second response, and then you have another inch of rainfall excess in the third period, and this would be the third response to it, and the fourth response. And so if this rain just kept coming and it never stopped, then the S-curve represents the total, or kind of it's looking at the cumulative effect of each one of these. And so what we need to do is have the sum of all of the columns to the left, including the first one. Okay, so as you drag it down, what you'll see is that it eventually comes up to some total, and it holds steady for a couple of periods, and we need to see that it gets up to this maximum flow rate if the storms were just back to back. Alright, so the next column, the lagged S-curve, you lag it by the number of periods that you want the new unit hydrograph to be. So in the problem statement it says that we're transforming it from a 2-hour to a 4-hour in this example. And so we're going to lag by T prime R, which is the desired storm duration of 4 hours. So it means copy this resulting S-curve, Control C, and then you paste it starting at 4 hours. So it's, somehow that didn't work, the S-curve, and then you paste it, paste the values, not the formula. Okay, so we created the S-curve by just having the back-to-back storms. We lagged it. Now we need to subtract the S-curve from the original S-curve. And so this next column we're going to call it the lagged 4-hour hydrograph. Okay, so it's going to be the S-curve minus the lagged S-curve. So equals S-curve minus lagged S-curve. Now where it goes into negative territory, we need to override it because there's no such thing as like a negative outflow. It's not like the water starts going back into the watershed. So we would just type 0 and drag that down. So again, what we did is we started with the S-curve and subtract the lagged S-curve. And then the last thing we have to do is divide by the ratio of the times. And so our original time was 2 hours, and our new time is 4 hours. So we're dividing this resultant hydrograph by T prime R, which is by 4 divided by 2. So we're dividing by 2, the ratio of the new to the old. And so then this is the 4-hour unit hydrograph. Okay, so it is the one to the left divided by 2. Now the question is, this is the same watershed, but what we're talking about is in the first, what we started off with was an inch of rainfall excess happens during a 2-hour period. And now what we're saying is the same watershed, the same amount of rainfall excess, but we're spreading it out over a longer time. So instead of having a higher intensity, that rainfall excess happens in 2 hours, what if it happens in 4 hours? And so if we just look, of course the peak is going to be less dramatic in terms of, it gets up to 69 right at the beginning of the storm compared to only 34. But let's do a figure just as a comparison of the two. If we make a chart, you can see that I had one on the paper handout that I gave you. So if we insert and make it a scatter plot, make it smooth just for illustration. And we'll have to select the data. So what we want to have is 2 different series. We'll start with the initial 2-hour hydrograph, and time will be on the x-axis and the runoff will be on the y-axis. Okay, and then we'll add another series that is the 4-hour hydrograph. Again, time on the horizontal, and then this 4-hour hydrograph. So the peak is a little bit lower. We're only going to see 370 instead of 389, and it shifts it to the right, but you can use this for a transition a lot more dramatic than a 2-hour to a 4-hour storm. You could use this to take a 1-hour rainfall excess that you have the hydrograph for and transform it to 8 or 12 or 16, and that would really bring the peak down quite a bit more than this transition. The same structure would hold, but the thing that I guess the takeaways from this is that there have to be enough of these columns that it reaches a constant value and then it goes down again, because when you lag it and you're going to be subtracting, if it doesn't reach this plateau value, then the hydrograph won't go back down to 0 when you lag it, the subtraction. Alright, so the procedure is here on the slide. Start with the S-curve. You subtract the lagged, you shift it, and then divide by the ratio. Any questions about that procedure? Okay. Well, that went quicker than I thought it would. I thought we would need more time for that, so that's why I rushed through.
Okay, so another question.
Yeah.
You've got total volume at the bottom of all these columns.
Oh, yeah. Relevant? Yeah, I'm glad you asked about that. So, it's the same amount of rainfall excess, it's just over a different time. And so, in theory, the storm volume should be the same if it's the same area of the watershed and it's the same amount of rainfall excess, all this procedure does is it's changing when it comes out of the watershed, because it's going to kind of meter it out from the sky onto the ground at a lower rate. And so the way that I calculated that runoff volume is, this is CFS, cubic feet per second. And so you think about in each of these increments, how many seconds are there. And so we could calculate a volume. If I copy this time again down here, so this is going to be time, and then over here is volume. So the volume for each increment is going to be the cubic feet per second times 2 hours times 3,600 seconds per hour. And so we could find out during each of these increments what volume accumulated during it, and then we could add it up and find what was the volume of the water coming out of the watershed during that 2-hour storm, just as a proof that it's not changing the amount of water that comes out of the watershed. So this is for the 2-hour. So now here's our 4-hour unit hydrograph. So I'm going to calculate the volume here, and it's the same time periods. And so for time 0, we had 0 flow rate. Times 2 hours, because this is still 2-hour intervals, even though it's the rainfall itself happens during a 4-hour time increment. What we're looking at is the runoff in 2-hour. Like, that's the resolution. That's the size of each increment. So 3,600 times 2. And if we add that up, hopefully it should be the same volume. Yeah, it is. So that's just kind of an illustration that this procedure doesn't affect the physical properties of the watershed. I like the comma there just to kind of show, but anyways, it's 14 million. This unit hydrograph method doesn't change the soil assumptions, it doesn't change the land use assumptions, it's just kind of changing when the precipitation is coming out of the sky and what will be the response of the watershed from that. So, are there any other questions about this procedure? So let's take a look at the homework assignment. All right, so here is a Snyder method homework problem, and what you can do is use the procedure and the example that I give you for the Snyder method to do that one. And then this is a given 4-hour unit hydrograph, and I'd like you to transform it into an 8-hour hydrograph using the same basic procedure that we just went through today. So the only difference being here that, you know, these are SI units, but that doesn't affect anything. Like, the structure of the procedure is the same. So, are there any other questions? All right, that's all I have for you today. I'll see you on Wednesday.